All right. So thank you everybody for coming, and thank you for the introduction. My name is Attapol, Thamrongrattanarit, and today we'll talk about gender bias in NLP. I take it that not everybody has a strong background in deep learning and NLP. NLP is a technology for processing a large amount of text and making sense of it, or automating language tasks as we know it. Usually we talk about machine translation, sentiment analysis, text understanding in general, or like summarization, question answering. Those are some of the examples of application of natural language processing. And the reason why I also have to talk about deep learning in this talk is that it's like one of the main technologies that power most of the NLP tasks that we are doing in the present days. So before we get to gender bias in NLP, so I have to talk a little bit about deep learning and what it is. Right? Deep learning is an algorithm that learns from some data. It doesn't have to be a large amount. It learns from the data. It has very sophisticated equation of how it translates text into something that computer can understand and try to make sense of it. And a very fundamental building block of language in general, and also deep learning, is meaning representation of a word. So what do I mean by that? So when we feed something into a deep learning algorithm, we need a good representation of a word. What is a good representation of a word? Something that can tell the machine that what the meaning of the word is. Okay, so meaning linguists have tried to theorize of how we could change text into representation of meaning. One of the first attempts is to recognize, feed into the machine what's the synonyms of what, what's the antonym of what, what's the opposite word, or the words that have similar meanings, or what's the hypernym, as in like X is some for the Y, or Y is a superset of X. So that's some quick overview of lexical semantics from the linguistics point of view. But nowadays, the model that we use to model meaning of a word is called word embedding, which I will talk about more extensively in this talk. So, what is a word embedding? It uses the idea from linear algebra, or we also call it word vectors. Word vectors is a representation which is essentially 100 numbers. We use 100 numbers, 300 numbers to represent the meaning of a word, which is kind of convenient because once things are in number form, computer can process that pretty easily, pretty well actually. So first step for doing anything related to language path NLP using the modern deep learning technology is that we need to have those word embeddings that represent the meaning of the words. Okay, that's a very quick overview of the current fundamental technology that powers basically all of the cutting edge research in natural language processing nowadays. Okay, that was very quick. Hopefully we can move this along. And let me share the screen. I prepare a little bit of slide for this talk. All right, since okay, so gender bias in NLP. So there are 4 things that I'll address in this talk. It's a source of gender bias, danger of gender bias, observing bias, and de-biasing in general. Okay, since when this has become an issue, right? NLP has become more relevant to the modern days, probably 10 or 20 years ago. Before this, it's just like toy technology. We don't see it in everyday life as much, right? But now we see it everywhere. We see it in search bars, in any website that you go to that has a search bar. it has some sort of NLP in it. Okay, so we got other things like Alexa, all the virtual assistants that we interact with nowadays. Also, and that's also NLP. Also use the modern technology. So people start to recognize the gender bias in NLP because it's more relevant to us, and it's time that we think about this kind of biases. So you could one of the first things people recognize is not gender bias, but it's like more racial kind of bias. So it's we first talk about this from computer vision, like an algorithm that recognizes the human face versus other objects, right? You probably saw some funny videos where an algorithm doesn't recognize African American as a person because the algorithm is biased. So that's a very clear indication that there's definitely a bias in making this technology into a product, right? So that's the beginning, and now people start thinking about other sources of bias. So we will talk about NLP today. One of the examples that I come across when I was working at LinkedIn before I moved back to Thailand and teach at Chula, is that when I was working at LinkedIn, that's the website for posting jobs and resumes. So we found preliminarily, we found a gender bias in search terms in general, especially in languages that are so gendered. For example, in German, you have one word for, say, teacher, for a male teacher, and another word for female teacher. So for most job posts, they don't require specifically that you have to be a male or female to do the job. So they will just usually they'll post a job in a male form. Okay, so when a female person or a person who uses the female version of teacher, so it's Lehrerin in German, it's Lehrer in the male version of it. So if you use the female version, then you would not get as many job posts. So if a user doesn't know that there's a bias in the system and naively search the female version out of like familiarity or for the correctness sake, then they might miss out on some opportunities. And then when the engineers discover this very obvious gender bias, we try to fix that quickly, but it's not that easy to put that to fix quickly because it's buried down in the system. So that's a personal anecdote of gender bias in NLP that I'll start with. But today I'll review some of the literature and how people have turned to raise this as an actual issue in research and in production in the industry, right? So like most of the work would be quite new because it's recently become it recently attract more attention from the research community. So you see just how they would only talk about like the newer technology, but not the older algorithms. So it's mostly deep learning. So that's the background before we get into it. So let's talk about source of gender bias, where it comes from. So there are multiple sources. So it's from the training data, from the word embedding, or from the model itself. So these three, they are obvious answer because to people who do machine learning and NLP, because these three components are very important components that we see in basically all systems, right? So training data, why is it a thing? Because for any system, usually it's a machine learning kind of system, which means we don't teach them specifically what to do. We train the model, as in we train the system from the training data. So we feed them a bunch of examples so that it learns from those examples and then try to do intelligent by learning from the data. So that's why training data is a very important source of it. But we'll see later in the studies that I'm going to present next that that people have proven that is actually the case. And secondly, word embedding, which I just told you about. Word embedding again is a n-dimensional vectors that have the property that preserve the syntactic and the semantic characteristic of each word. So both grammar of the word and the meaning of the word all together in compact, three-dimensional vector. So 300 numbers. If you don't know what vectors are, yeah, there are 300 numbers that can together can keep the meaning of the word. It's a pretty strange idea, but I don't think I can talk about embedding for hours, but I just want to give just an overview of what it is. So why it becomes a source of gender bias is that now it becomes such a common resource. What do I mean by a common resource? So whenever you want to train any model and you want to make it smart, you download word embedding from somewhere. There'll be like 4 or 5 favorite versions of word embedding that people usually download from and use them off the shelf without doing anything. So if there's a bias in there, the bias will propagate into the system. So that's another resource that could be a source of gender bias. And the third one is the model itself, which is less of a problem as we will see next. So people have classified, what kind of gender bias it can be. We might expect to find in real use. So the danger of it is that it reinforces stereotypes in the downstream applications. There'll be more examples coming, and sometimes it will produce the prediction that have the gender bias in it, and then amplify the biases in the training set. Because sometimes to generate the training set, you use the model that has the bias already. So the prediction for the model will propagate right into the training set for the next model to come. So yeah, so we have to trace back to the very source of it, right? So the biases can be categorized in terms of the allocation bias, as in, as like an example I told you before. So the system will unfairly allocate resources to certain groups over others. If a female person if a person uses female terms or gender terms to search for a job and it returns fewer results, then they are less likely to get the opportunity the job opportunity that they want, right? And secondly, representation bias is just detract from the social identity and representation of certain groups. So yeah, they in the talk by Crawford 2017, they compile the representation bias in the context of gender or gender bias, and they try to classify them into 4 categories. So denigration, stereotyping, recognition, and underrepresentation. So if this is quite embarrassing kind of error actually. If you use machine translation and you translate, we call this back translation. If you translate English sentence, he's a nurse, she's a doctor, this is totally fine, right? Because anyone can be a nurse, anyone can be a doctor in a perfectly unbiased world, right? So if you translate that to say Hungarian and back translate it into English, okay, then you get things like she is a nurse, he is a doctor, because Hungarian might not have a gender pronoun, okay, or the verb that they conjugate might not preserve the gender in it. So how does it solve that problem? It goes for intuitive judgment. So now machine hasn't got intuitive judgment, so it translates back to she is a nurse, he's a doctor. So that's a gender bias, right? Because stereotypically, right? So that's why they have to tick on the S. Stereotypically, a nurse is a female person and doctor is a male person usually. And by saying that, I'm already stereotyping, right? And also recognition, because it's actually an error. So if you have a source sentence, like in English, and you translate it to Hungarian, when you translate it back, it should have the exact same sentence back. But now it deviates from the correct sentence, right? So that's why we get both biases for this kind of passage, machine translation. That's essentially a classic translation error, because pronouns, not every language has different pronoun systems. Some are very gendered, some it's not so gendered. So that's a classic translation problem, because the pronoun systems vary by languages. For the next task, we have caption generation task. So what does it mean? So if you have an image and you want a system to generate captions, quite straightforward, right? So if there's an image captioning model incorrectly predicts the agent to be male because there's a computer nearby. So having a computer nearby has nothing to do with the gender of a person or an agent that needs to be recognized by the machine. Since it cannot rely on other cues, they're more likely to classify that person as a male, because computers usually associated with male. Then it already feels weird saying that out loud, actually. So that's also like the same problem, right? So it's stereotyping people that are close to computers most likely, are stereotypically male. And that's also a recognition error, because the machine makes actually an honest error, because it should not be. It makes a wrong prediction, right? Speech recognition, so it can be underrepresentation kind of problem too. So in Chapman 2017, they found that the speech detection system worked better with male voices than female voices. Like very similar to the example that I gave earlier about an algorithm that would detect a human versus non-human. So yeah, in this study they found that this kind of system works better for male voices. So that's an underrepresentation problem, because usually it depends on the data that you feed in. And again, sentiment analysis ranks sentences containing female noun phrases to be indicative of anger more often than sentences containing more male noun phrases. That's another example. And a language model, which you'll see more actually in this talk. A language model is a model that gives you a score of how representative that sentence is of a language. So it gives a probability of seeing that sentence in a language. All right, language model, usually talk about it for 2 weeks for somebody to understand, but that's the gist of it. So they found that the sentence "he's doctor" has a higher probability than "she is a doctor." Why? Because they see that more in the data. So the bias is actually in the data, but it shows up in the output of it. All right, so these are some of the examples that people have found to be problematic in terms of gender biases. So how do we know? What are the methodology of doing that? So we do something very close to a classic psychological test called implicit association test. So in IAT, implicit association test, participants are asked to make some sort of association task, and when so you can measure the association between concepts and like evaluation or stereotypes. So if the brain thinks that they go together, say black and athletic, if they think that that goes well together, you see lower reaction time because that means the brain has to process that less when they need to make that pairing. But again, I'm not going through the detailed IAT, but the gist of it is that it measures the association for each person that does the test. So the main idea, oh yeah, I already said that, right? So yeah, you can test each person's stereotype. That I think in this association test, if you Google, you can do it for all sorts of biases that you could think of, like gender, racial, for each occupation, even they have like a very long-standing study. I think it's done at Harvard. That's a classic psychology actually. So we do something like quite similar, but not with humans. So we use word embedding to measure the association between each concept with male or female, but you can do it for most concepts as well. So in this study, they take the word embeddings that are male related, like male, men, boys, man, for example, but they have a set of words that signify a male, okay? And they have another set such as like female, woman, women, girl, girls. Those are all the female words, rightfully so, right? And then you compute the similarity of the male words with each, say, occupations or names, okay? So what they found is that the association of say male and female are almost perfectly correlated with the actual percentage of workers in each occupation. For the graph on the left, the x-axis is the percentage of workers that are in that occupation. So each dot is each occupation that they test with, and on the y-axis they test the association using the word embedding, like plumbers, doctors, construction workers, or all and the occupation that they have the data for. So you can see that the association has a very strong correlation of 0.9. It's very rare that you can see that kind of correlation in most data sets. Actually, if you have some statistics background, it's very hard to find an actual data set that has that strong association. But we indeed have that kind of strong association. So what it means is that the word embeddings, so like the thing that represent the meaning and also the grammar of each word, actually absorbs, actually encapsulates, actually registers the percentage of workers in that occupation in each gender. So it's already been absorbed in that. So once you take that word embedding and put it in any downstream model, that kind of bias is going to propagate. So they use this test to pinpoint that this is actually a problem, and it's actually in the word embeddings already before we even do any kind of modeling. Okay, so on the right, they do similar things, but they do it with names because it's pretty clear, right? It's very hard to find a male person whose name say like Susan or Mary or Linda. There are names that are stereotypically male and female, although technically there should not be anything that stops you from for a male person to name themselves say Cherry. That's nothing to stop them, right? But that's what the data shows that stereotypical names for male and female do exist, and the word embeddings, we also have the embedding for each individual name also absorbs that. Okay. All right, so we have established that we will look at these embeddings, because these embeddings are we have proven that there are gender biases in them. So once we can identify the gender bias in it, like say, each occupation, because it should be 50-50, right? It should not be strongly associated with one gender more than the other. If we want an NLP system that has no such bias, so that leads to a whole new line of research. Actually, started probably 10 years ago. It's quite a new issue to do de-biasing. So people come up with all sorts of algorithms that will de-bias the word embeddings in particular. So that's the first line of attack for them. So hard de-biasing, so there are two types: hard de-biasing and soft de-biasing. So there's a neutralizing kind, so it ensures that gender neutral words as zero are zero in the gender subspace when we try to project it onto the other occupations. It should be quite neutral, and it should equalize set of words outside of subspace and enforce the property that any neutral word is equidistant to everything. Okay, that's a hard de-biasing, which we won't do as much, but most likely we'll do soft de-biasing. So we do any kind of de-biasing we want, but at the end of the day, though, we need to preserve original properties, because word embeddings are very important. It's a building block for most models. So if in this process you de-bias it and it messes up anything, so then there's no point in using these word embeddings anymore. So that's the challenge of de-biasing line of research. So in this study, like for example, they have to look at hard bias and de-bias. So we should have this kind of results, right? So we on each column we have RG, which is the training set of sorts, which I won't talk about. We have word similarity, WS, and analogy tests. Those are the tests that will test whether the word embeddings that we are using are effective or not. Okay, so it turns out that we could successfully run the de-biasing algorithm and make no significant changes one way or the other onto the benchmark data set that we use to assess the performance or the accuracy of the word embedding. So that's good news, and that's the kind of algorithm that we want. Okay, so what about the performance, right? If you look at it on the more on the performance side, sorry, I won't get into much of the algorithm, but it's some metric, which I don't think it would make much sense if you if you haven't seen the equation for word embedding. So sorry, I need to skip those for now. So, but if you have more questions, I could send you the references. Okay, so another idea is to do this is to if you notice that there are recognition problems. So for male and female people who use the system, they should be able to expect the same kind of performance, the same kind of accuracy, right? Like when back to the example that I gave from LinkedIn, if you use the female version of the job versus the female version of the job, you should get the exact same performance. Or in speech recognition, if you use if a male user with a male voice uses the system, you should have the same accuracy as a female counterpart. Okay, so that's another bias that we will try to measure. So yeah, so the model prediction should not be influenced by the gender or the dimensions or the context that are so gendered. So for example, if you say perform sentiment analysis, you want to know whether a sentence reflects positive or negative attitude, you should get the same label regardless. Okay. So for example, he went to the park versus she went to the park. For any label, for any classifier, for any system that you use, it should produce exact same output because there's no reason why it should not. Okay, except when you want to translate this. Maybe you want to use the, say like Korean male pronoun to be translation for he, and the female one for the translation for she. And that's fair, but for a classification task when you try to put a label on a sentence or on a piece of text, it should produce exact same output. So within this slide, they come up with gender bias evaluation test set, GBET, which become actually a very important benchmark for design research. So they got a bunch of data sets that they collect. They call it Wiener gender schema, which come from Winograd schema. So they changed to Wiener to Wiener gender, and that's I guess clever. So the task is co-reference resolution. So you could see if it performed differently or not when they try to resolve co-reference. What is co-reference resolution? Real quick, it's a very important task in NLP. So it tries to resolve nouns that are, that we want to know what it refers to. One important case of it is pronoun resolution. He, she, it, and they, and we. We want to resolve what they refer to in the text. Okay. So sometimes it's not so clear, what it should refers to. So we built a very complicated deep learning algorithm actually to perform co-reference resolution. It's a very challenging task to begin with. So if you want to avoid gender biases as well, it would be even harder. But it's still worth doing because you make the system more accurate. Okay. So they collect a few evaluation tests and and make it like a standard benchmark for evaluating whether an algorithm has bias or not. Okay. And they also have a sentiment analysis task. So you could probe it with emotion. So on the third axis, on the third column, sorry, they have probing concepts. What does that mean, right? We could try to basically probe it, like trick the system, like whether he will be more likely to be resolved to a doctor or not, when it's kind of ambiguous from the sentence, or she is more likely to be resolved to a nurse, for example. But I'll have more example with next slide. And for names as well, if there are, you can also like probe it with names, or you can probe it with emotion, because there are some stereotypical emotions that are stereotypically associated with one gender or the other. Okay. All right. We know gender schema, and it's actually like very interesting. So it comes from like Winograd schema, which kind of tests very high level understanding of language. In Winograd schema, we think that if a system can solve Winograd schema, the system actually understands language and understand the meaning of language. Okay. So let's look at some examples of Wiener gender schema. So they twist that and make it more gendered. So let's look at 1A. So there's occupation and participant, right? So paramedic perform CPR to resuscitate somebody when they pass out, stop breathing. On passenger, even though he, she, they know it was too late, right? So in this schema, though, it doesn't matter whether it's he, she, or they, or even he, she, or they there. It should all refer to the paramedic, right? Because the passenger is already passed out on the floor. If they cannot possibly know, it's too late. So Winograd schema would be something like this, where if you know the meaning of the sentence, you should know exactly that that pronoun should be resolved to the paramedic and not the passenger. But in Reno gender, they twist it a little bit and test it on he, she, and they, on all gender and non-gender pronouns. Okay. And then on the 2A, again, paramedic perform CPR on the passenger, even though he, she, they was already dead. Again, it's very clear for humans anyway. For computers, it's still quite difficult that the pronoun should be resolved to the passenger, right? So yeah, so in these cases, for 1B, they make it a little bit more vague, right? By replacing the passenger with someone, and same for 2B. It's the same version of 2A. It's very similar to 2A, but they changed one word. Okay, so what we should see is that he, she, and they in English, they can also be used instead of he and she when you don't know the gender of the person, because paramedic can be anybody, right? If you haven't seen them or know exactly what gender they identify with or what pronoun they want to use, then you use they. It's pretty safe. Okay, so they become a singular, gender neutral pronoun, which some native speakers reject, some accept that, but I think become more acceptable nowadays to use they. It's still followed by are, right? But they can also refer to a singular non-gendered person. Okay. So that's a Reno gender schema. So if we test co-reference solution system, then we could see whether it's biased or not. So in this study, they test three types. That's a rule-based kind. So you write up the rules on how to resolve it. Usually, you go back to the previous sentence and see if the subject actually agrees with the pronoun. For example, paramedic. That's a candidate for resolving the pronouns, and it agrees with he and she, because paramedic is singular, and it can be he, it can be she, but we can code that indirectly that it can be the case. Okay, and for statistical, we will learn from the data whether it should be resolved to those noun phrases, and then we use neural network, which is a deep learning technology that we actually use nowadays to perform co-reference resolution. Okay, so from these plots, it actually turns out that the system is actually more biased toward one gender over the other. So yeah, it's not super surprising, right? Because we haven't done anything to de-bias it yet. So most likely, if you use embeddings that are already biased, very likely that you will get the biased results. Okay, so those are some attempts, right? Because if we have a way to know and also a way to measure whether we are biased or not, then it's very easy to make progress. And that's the logic of NLP research. We have the standard benchmark data set. We have the metric that measures what we want. In this case, the metric that measures gender biases. So we have these sets. So we can come up with more algorithms, and we can test them out whether we are successful in eliminating the bias or not, or de-bias the system or not. So there are two kinds. The second kind we already talked about briefly. So we can de-bias in the word embeddings themselves after you already trained the word embeddings. But you can also de-bias on the training corpora as well. As I said before, since most modern systems that we use in NLP now are machine learning, so it needs data, and most likely you will need the word embeddings as well. So we will attack these two sources first, but let's look at how we can de-bias the training corpora so that it doesn't propagate the generative biases onto the downstream path. Okay, so we could use this technique called data augmentation. Data augmentation means we generate more data. So usually in the training data, that means the data that we use to make the model smart, the data that the model would ingest or learn from to make itself smarter. That's the mantra of machine learning. So we try to augment it. What does it mean? We try to first with it. Modify it, usually we try not to do that unless we have a very good reason for it. And this is one of the good reasons for it. So we try to augment it. So we try to make the data more gender balanced. So how you do that? They try that out with gap corpus. So they have the co-reference label pair that means ambiguous pronoun and antecedent name, right? Sample from Wikipedia and used for co-reference resolution. So for example, I voted for Nader because he was most aligned with my values. So he, if you have more of these data and you see the name Nader, Nader, and it got resolved to he more often, so the model is going to learn that. It's very hard to stop the model from doing that actually. So because it uses statistics, right? What they see the most becomes knowledge. So if it sees that he is associated with the name Nader more often, it's going to have that bias, and there's no way around it. And the way around it, so I was wrong, there's some way around it. That is, you generate another set of this and put it and add it to it and change he to she and change it to the training set. Okay, because Nader is actually kind of a rare name. If you ask an American or a British person, they would not know exactly what if a Nader to be a male or female, right? So they de-bias it by when they see that a name is connected to a pronoun, add another instance so that it balances itself out. Okay, but for the red one, it doesn't matter, like she and mine and I, right? So Birch. So yeah. So the problem. So another example for de-biasing it is to change something in the model. So the problem is that we want to observe and measure the bias and also and try to mitigate this problem in BERT. What is BERT? Like you ask. BERT. Usually, BERT I will talk about it, for like 3 hours. So for most students to actually understand briefly what it is. What BERT is for now is just a very, very good system that actually revolutionized the field of NLP 5 years ago. It got revolutionized twice since I started doing NLP. Lucky for me, I guess. So you can just think about BERT as like the best model that we have so far for NLP. It's used for most things nowadays. So since it's such an important model, so we want to make sure that it's actually good and potentially bias-free. So first we have to probe it and try to observe the bias in it and then mitigate it later. So BERT usually is trained on billions of words of data. Okay, billions of words of data is large amount, more than we can imagine that a human brain could imagine, how much that is. We could imagine like 500 words, right? Which is like, a few pages of essays, that's 500 words, right? But when you talk about like billions, we could not really imagine how much it is, but it's a lot. Just think more than we could possibly read in one lifetime, okay? So usually BERT is trained on a large amount of data. So since it's trained on the data, we can also debias it by changing the data as well. So to do that, you could also fine-tuning using math data. So how do they do that for this? So if you have a task like this, right? When you have a target, let's say like sun is a very male word, okay? So usually when you train BERT, you try to make the model guess what word is in the mask. So you hide it and try to make the model guess what it is, guess what that word is, right? There can be many, right? There can be anything in there, like my son, my daughter, my wife, my husband, there's a lot of words that can go into there. But you force BERT to learn from the context what word is in that position, and that's what makes BERT smart, right? It's have a lot of exercises in guessing words that are missing, like closed tests that we did in entrance exam and whatnot, right? So yeah, so it's just a bunch of closed tests, and if you don't do anything to it, of course, it will try to absorb the statistics in the language, in the data. So most likely, it will guess the word that's in the mask to be some male words. And that's not what we want, right? That means that the system encodes this bias somewhere. So we could also mask the attribute. So like, if you have the structure, my blank is a blah, 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 you could mask all of that, right? So most likely, if you do that using just mask the attribute, it will try to learn something that's like associated with sun, which is male word, right? So if you mask both target and attribute, then you have a chance of debiasing it. So I think this is like observed again and again. So if you mask the place where a gender word could go to, it will put in some stereotypical words. Okay. So for the first step, when you try to debias BERT, you get a sentence with both target and attribute. So it is in this structure. It's a kindergarten teacher, right? So you have target he, and you have kindergarten teacher, which is the attribute. So you mask target word, and then you try to find the probability of that being he. All right, and you could also mask both target and attribute words, and in compound mask each component separately. So you have mask is a mask. So and then you can obtain the probability of target word when the attribute is masked, and then you can compute the association. So I'm gonna skip on these. So you could see like the biases that I described earlier. It will put in he when they see the attributes that are stereotypically male. So to do that, how do you do that? So there's a bunch of ways that we can again augment the data, which means we will modify the data in some way that will eliminate the gender biases. So you could use the name base counterfactual data. So you can substitute some of the names so that it balances out, right? So like you could use the name that are, if you see the name that are male, you can substitute it to the name that are female, and that's usually quite easy to do because you have to do this automatically for a large amount of text. So for the gender of word denoting person, you can swap in place in order to counterbalance the bias. So you get more data. So you get a copy of it that's of opposite gender, and you also replace the first name. Okay, so there are a bunch of things you can do. These are some obvious things, right? These are some preliminary work. Okay, so here's the results. So on the top, right? We on the x-axis we have each occupation that are usually quite stereotypical of one gender or the other, and so we have carpenter, and you can label that yourself, whether one is more biased toward male or female, right? Like roofer, plumber, steel worker. Usually they are stereotypically very manly occupations. So if you look at the result from the figure, the top one, you can see that it's very biased, right? So it's more so it favor one gender over the other when you look at the association. Okay, so that's not good. So you see the biases, but after de-biases by modifying the training corpora in the way that I just described before, replacing the names and duplicate the data, replacing the names, duplicate the data, changing the pronouns. That's actually quite effective because so you can see that the association actually go hand in hand now, right? So before you see that it's negative for female and positive for male. So it's going in different directions, positive or negative. But now you can see either both negative or both positive in almost equal amounts. So that's actually a success. So we could actually debias the model itself because you change the data and then the model behaves differently. So when you look at statistically, they don't say stereotypically. They actually look at the number of people, the number of people that hold each profession, and count the percentage of each. And these are statistically female professions, housekeeper, receptionist, secretary, and so on. So you can see that before you debias it, you see that the association goes in a very different direction, right? So for say housekeeper, the association is more toward female and negatively toward male. So that indicates the gender bias. But after fine tuning, as in fine tune with the corpora that we modify in a way that I described before, the gender biases kind of go away. So that's good news. So just for one more example, I think we still have a little bit of time. For machine translation, that gender bias is not the only problem in machine translation. You can see many other translation errors, right? Because it's still quite not so mature for real application for machine translation. So we could do something that's like gender tagging, can tag it so that when you translate, it behaves in a gender unbiased kind of way. So, but we think that like masking, that's in masking it might decrease the accuracy for machine translation. What we found though is that MT as in machine translation mostly predict the source to be male because training sets are dominated by male source data. So when it doesn't know what gender it should be, it would just try to get something male related. Because there's more of those. There are more of those in the data. So we just hope that gender tagging would mitigate this by adding a tag indicating gender of the source of the data point, and then increase the gender awareness for the model. So let's expand more on this idea of gender the tagging onto the data. I think I'll show the data in the coming slide. So yeah, grammatical gender, huge problem because it's almost impossible because sometimes you just don't know. In one language, it might not so gendered. It might not be so clear what gender it is. So when you translate it, it's most likely to be a he. It's most likely to be some male-related thing. So that's a problem of underrepresentation in the data. So to do that, you try to tag it as in like a non-word. You kind of tag it into the data so that it will learn the association. And we try that with English to Spanish and English to German translation to see what happens. So for example, if you have an English source, the trainer finished his work. Trainer in English is not gendered, but in German it's Trainer or Trainer because they have the in suffix to make a word that ends with an er that is male into a female version. So you can see that the article there and D, there is for male, D is for female, and seine, it means his, and ihre, it means her. Okay, so that's kind of consistent for the English source, right? But for when you translate like this, the trainer finished their work, there and it's not. So there, as I said before, there's gender neutral because if you don't know whether your trainer might be like your personal trainer, right? What gender they are, then there's a very big, don't in English to be nice, to be politically correct, or to be nice. Let's say to be nice. If you don't know it, don't guess the gender because if it's wrong, it can be very offensive, and that's not a very nice thing to do. So sometimes we use there. All right. So so for his and her, it's quite easy, right? Because then if it's his work, then you know that trainer should be male or identify himself as male. When it's there, we should change it to something like this, as in definite pronoun, and trainer will think later whether we should change it to a word ending the suffix that make it a female or not. And then PRP, that's the possessive adjective, right? Which we don't know where we should put in either. So a good system that outputs this should give you an output like this, right? That are so gender neutral in German. Okay. So yeah, that's the idea of like tagging the scheme. So that's so you change this directly, right? So so for this, we could do something like when you have to really enforce it. So we could have this version of V1 where when they test whether if you tag it directly, that trainer male, because it's very clear for the context. So that is more reinforced when you see this in other contexts, it might then it can translate it correctly. Or if you have a mixed thing like this, like the trainer and the choreographer finish the work, you can tag it whether one is neutral, one is female, and you could do something like this as well. The trainer tag it as female, and the choreographer is a neutral. So when you translate it, trainer, the tag of female can be directly translated to trainerhund, which is the female version of trainer. And for the choreographer, I think that there are two versions that change the ending for choreographer in German. I don't know German that well to know what the words are for German. And similarly for Spanish, if you know Spanish, you probably know what it's talking about. But yeah, but you can see that the word takes different ending for the male version and for the female version. So yes, so it turns out when you augment the data with tags that we do it in V3 and V4. So this version, the accuracy actually go up, which is nice. So it's not only to debias the model just for the sake of gender inequality, equality and whatnot, right? But it actually makes the output better. So it's not a social issue. It's also a technical issue that we need to recognize and then that we need to solve to make the system more accurate. Get this part. All right. Okay, I think we've that's the last sample I have. So yeah. So these are, to recap what I said before, I basically just review some of the newer works that we see in NLP research. Gender bias has been recognized as another research topic that more people have been looking at and try to address. And the biases are usually come from the data that we use to train any kind of model we want. So we can see that one way to address that is to augment the data. First, try to recognize where the biases are, and then you try to counterbalance it by adding more data to it, which is called data augmentation. So, and also another way, which we have seen with word embedding, is that they use the metric so that the word embedding for the female and the male version become more similar, and while preserving all of the characteristics of the word embedding that we see in the bias version. So we want to keep the accuracy intact, if not improving as well. So all in all, we can see that these are not just the source of bias, it's also the source of error. So while solving this, we not only make the society a little bit nicer, but we also make the system more accurate and making progress in NLP advances. So that's all I have today.